All right, welcome back, everyone. So just to remind you, when we finished off last time was talking about properties of vectors, and we finished off with multiplication of vectors. So again, there are three ways to multiply vectors. The first way is by scalar. The second way is what's known as a scalar or dot product. And this is when you multiply two vectors together to actually create a scalar. We'll talk more about this later. And then the third way is what's known as a cross or a vector product. So as again, I mentioned last time, these two here, the scalar product and a cross product, we'll save these for later. And we'll talk about these when we actually need them. But for now, we're going to focus on the first one, which is multiplication by scalar. So what does that mean? So let's say that we have a vector, and let's say we have some sort of vector A. So let me draw my coordinate system here. So here's my coordinate system, and then here is my vector A. And what I want to do is create a new vector from that. And let's make some new vector. Let's call it vector B. Okay, so this is vector B, where vector B is going to be some constant C times then R. Well, C is a real number. So this is inside of the real numbers. So basically, we have three options, right? So option number one is that our scalar quantity here can be some sort of positive value, but less than 1. So what I mean by that is option number one is that, for example, C is somewhere between 0 and 1. Right? So as a concrete example, let's say C is simply equal to 1/2. So in this case, what we're saying is then that B is equal to 1/2 of C. So what happens? So in this case, what happens then is that B is going to point in exactly the same orientation as vector A, except it's going to have half the magnitude of A. So it's going to be half the length of A. So in this case, the orientation is still going to be the same, which means that the angle theta B will still be equal to angle theta A, except in this case, now the magnitude of theta B is going to be equal to 1/2 of the magnitude of theta A, or of vector A. So that's option number one. Option number two, I'll write that over here, is that C is bigger than 1. Right? So basically, in this case, let's say that C, again, is a real number, but it's going to be bigger than 1. Right? What happens in that case? So, for example, let's say C is equal to 2. Okay. So what happens in that case then is that the vector, based off of the other one, is going to have exactly the same orientation, except now it's going to be twice the length. So in this case, again, theta B is going to be equal to, again, exactly equal to theta A, but the magnitude in this case of vector B will be exactly twice the size of vector A. So in this case, what it does is multiplying by a positive constant is either going to shrink the vector down whenever it's less than 1, that's option number one, or number two, it's going to increase the size of it, but it's always going to point in exactly the same orientation. So again, here, what it does is it grows the size of the vector. And then for the first case, it actually shrinks the size of the vector. Now, the third option is, of course, if this guy is actually negative. So let me redraw. So let's say here. Again, let me draw vector A. So again, here's vector A. And now let's look at, again, vector B. So B, again, is equal to C times vector A. But now for option number 3, and I'll draw that in green since I haven't done green yet. So in this case, let's say C is less than 0. So C is some sort of negative quantity. And again, for example, let's say I do C is equal to -2. For funsies. So what happens in this case? Well, what happens in this case then is, based off what we've known before, the 2 here, at least the absolute value of C, is going to cause this thing to grow twice the size of vector A, but the negative sign here actually causes it to rotate by 180 degrees. So what is happening then is that vector B is going to point in the opposite direction of that of vector A, and in this case, be twice the size of vector A, because the magnitude of C makes it then twice the size. So basically, what we see here is under this example, vector B, its angle then is going to be equal to the angle theta A plus 180 degrees, since it gets rotated by 180 degrees. So this angle here is 180 degrees, or simply pi radians. And the magnitude of vector B then will again be equal to twice the length, or twice the size, or 2 times the magnitude of vector A. Now, this is only true technically in 2 dimensions. What actually happens in 3 dimensions is it doesn't just get rotated by 180 degrees, it actually gets reflected through the origin. So what happens in that case then is it gets rotated 180 degrees by the 2 different angles. Basically, the theta angle and the phi angle both get rotated by 180 degrees. In 3 dimensions. But so again, we'll make a note out of that. So again, in 2 dimensions, this is true. So let's put a flag here. So this is technically only true. In 2D, so again, in 3D, it gets reflected through the origin. We know that because as we talked about when we talked about vectors, so again, in 2 dimensions, we only need 2 pieces of information to clarify or specify a particular vector. That's its magnitude and its angle. But in 3 dimensions, we need 2 angles and 1 because we need, or in the magnitude because we need 3 pieces of information. So through the origin. So this is multiplication. So that brings us back to addition, of course, where we can now think about subtraction. So let's look at vector subtraction. So vector subtraction then is actually just addition with multiplication. So what does this mean? So what this means then is we can think about the fact that if I wanted to take a vector A and subtract vector B from that, well, that's actually equivalent to then to vector A plus -1 times vector B. So if this is my resultant vector that I'm looking at, what that means then is I'm going to simply take vector A, add that to a rotated by 180 degrees vector B. So again, let's look at our tip to tail method and see what that actually means. So again, let's say here are my 2 vectors, the same ones we looked at before. So we have vector A pointing off in this direction, and then vector B was pointing off in this direction. So first, I can actually do -B by, again, rotating B here by 180 degrees. So it's going to point down in this direction. So this is going to be -B. So first thing I'm going to do is rotate B by 180 degrees. And then when I come up with the addition of these 2 guys together, all I'm going to do is add from the tip of vector A, the tail of -B, or the 180 degree rotated B. So again, if here's my coordinate system, so again, here is my vector A, simply copying that guy down. Now from the tail, or from the tip of vector A, I'm going to draw the tail of -B, which is the rotated by 180 degrees. And then my resultant vector, R here, is going to be the vector which points, again, from the tail of the first vector to the tip of the last vector. And we can actually draw a straight line. There we go. So let's try that again. There we go. That's better. So this is my vector R. So again, my vector R in this case is vector A minus then vector B, where again, minus just means we rotate it by 180 degrees by multiplying by -1, and then add to that to vector A. Now again, this is only true in 2 dimensions, but that's fine. So these are our properties. So we have the property of addition, where addition is commutative. Now, since subtraction is also just addition, that means that's also commutative. So it doesn't matter the order in which I add these together. And then we have multiplication, or at least multiplication by scalar, which does 2 things. So it either increases the length of it or decreases the length of it and rotates by 180 degrees, or leaves it alone, depending on if it's a positive quantity or a negative quantity. So good. So now we've looked at tip to tail methods. We've looked at the addition of vectors, multiplication of vectors. So now we can think about, well, how do I actually add these guys in a practical way? So let's say I wanted to add two vectors together or more vectors together, and I want to add them in a practical way. So what we've seen so far is only the graphical or geometric way of adding them together, this tip to tail method, which means that if I wanted to add them together, I would actually have to do what? I would have to bring a protractor, I would have to bring a ruler, I would have to draw these things out precisely, measure all my distances, and make sure everything is great and life is beautiful. Well, I mean, that's fine, but it's not exactly a very practical or very precise mathematical way of actually adding vectors together. So a better way to add vectors together is to actually break it down into what are known as components. So let's look at vector components. So what are vector components? Well, a vector component is you draw some sort of coordinate system. And again, we would draw our vector. So let's say here's our vector A. So a vector component is using that trig that we talked about during the first week, is actually just looking at the projection of the vector onto a particular axis. So what do I mean by that? Well, imagine that I had a flashlight up here or a light bulb shining down on top of this vector, and I'm going to look at how, or the size of the shade that is then created by this light. So what that means is this light is coming down. What that's going to do then is this vector here is going to block this light, which is then going to create a shadow onto this axis. So for now, let's just call this the x-axis. So here I'm going to cause a shade along this x-axis, and then the component of this vector along the x-axis then is simply the length of the shade. Now, if I move my light over to this side, and I do the same thing, so now here's my lights, what's going to happen again is I'm going to create a shade by dropping a perpendicular here. There we go. So this is 90 degrees. This is also 90 degrees. And then this component, which we're going to call the y component, then is then equal to the length of the shadow along this particular axis here, which is our y-axis. So this amount here is what we call AX, and then this amount here is what we call AY, which again is the amount of the vector along this particular axis. And let's say this is at an angle of theta A. So notice what we did here is we actually just created what? A triangle. So this part here, which has a length, which is called the magnitude of vector A. And then here, this is then the, according to this angle, the opposite side, and then this is the adjacent side. So we can find then the components of this vector by simply using the trig that we talked about before. So here, remember that we said that sine of theta A was equal to the opposite side divided by the hypotenuse. Here, our hypotenuse is simply the length of this vector, which is the magnitude of vector A, and then the opposite side is the AY portion. For cosine, we then have that cosine of theta A is then equal to the adjacent side divided by the hypotenuse, which in this case, the adjacent side is A sub x, that's the length of the shadow on the x-axis, divided by the magnitude of vector A. So from here, we can see then that according to this angle here, so remember we have to be careful of our angles, says that the y component is then equal to the magnitude of vector A times sine of the angle of the vector, and then AX is then simply equal to the magnitude of vector A times then cosine of that angle. And again, notice here, if I take AX squared plus AY squared, and I square root it, that's exactly equal to the magnitude of the vector. So the magnitude of the vector is actually the x component squared plus the y component squared, again, based off that trig that we talked about before. And then I can find the angle of the vector itself by noting that, again, using tangent, that the tangent of theta A is equal to the opposite side, which is AY divided by AX, which means that theta A is simply equal to the inverse tangent of AY divided by AX. So this is how we would actually find the components. So when we add the vectors together, it's much better to do it in terms of these components because the components is a much more precise mathematical representation as opposed to this picture where I have to measure everything in a much more precise way. Now, once I do that, then I can represent any vector in what's known as unit vector notation. So let's go look at unit vector notation. So if I know, for example, the vector has ax along the x-axis, and it has ay along the y-axis, and it has az along the z-axis, we can then define what are called unit vectors. So what's a unit vector? So if this is my x-axis, this is my y-axis, and this is my z-axis, the unit vectors then are vectors which point along the x-axis, which I'm going to call I hats, a vector which points along the y-axis, which is called j hats, and a vector which points along the z-axis, which is called, k hats. Okay. So these vectors, what are known as unit vectors, specify the direction of our coordinate system. So what I know is the x-axis lies along the direction of I, the y-axis lies along the direction of j, the z-axis lies along the direction of k. But these guys are called unit vectors because the magnitude of each one of these guys is simply equal to 1. So if I took the magnitude of I, that's equal to the magnitude of j, which is equal to the magnitude of k, which is then equal to simply 1. So if I had some sort of vector, which in this case I'm drawing a 3-dimensional vector, so let's say this is my vector A, then I can specify this vector in terms of these unit vectors by saying that vector A then is simply equal to the amount at which it is along the x-axis pointing in the x direction. So this is the amount AX pointing in the x direction. So the I hat tells me it's pointing in the x direction, plus the amount in the j direction or in the y direction. So this is my AY pointing in the y direction. So that's my j hat, plus the amount it is in the z direction pointing in the z direction. So this is in 3 dimensions. If I had simply a 2-dimensional vector, so let me go ahead and draw a 2-dimensional vector. So again, here's my coordinate system. Let's call this the x direction, y direction. Let's call this our usual vector A. So in this case, I would represent vector A by simply saying A then is equal to AX in the I hat direction plus AY in the J hat direction. Where again, AX would be the projection or dropping a perpendicular onto the x-axis. AY then would be the projection or dropping a perpendicular onto the y-axis. So this amount here would be equal to AX. Oops. There we go. And then this amount here would be equal to AY. So why does this matter? Well, it turns out that, as I mentioned before, a vector isn't fully specified until I put it into some sort of coordinate system, which means that coordinate systems are non-unique. Vectors are unique in the fact that they point in a particular direction. This vector will be the same vector, this vector A, regardless of what coordinate system I put it into. But my coordinate system is usually dictated by an observer who is watching what's happening. So what does that mean? So what that means is I might be watching this vector, like for example, this could be an acceleration vector pointing off in this direction, but somebody else might watch it so that they set up a natural coordinate system which is pointing this way, so that this is their x prime direction, and then this is their y prime direction. And then they're going to see this vector slightly differently in the fact that I see a certain amount in the x direction and in the y direction. But if I look at this observer here, this one, if I drop a perpendicular onto this axis, sees a different amount than I do along their x direction. And if I drop a perpendicular down in this direction onto the y-axis, they also see a different amount in that axis. So for example, this amount here is then the amount in this coordinate system. I'm going to call that AX prime. And then this amount here is that amount in this direction, which is then AY prime. So this observer, the yellow observer here, would say that, well, the vector A is actually specified by then AX prime in the I prime direction plus AY prime in the J prime direction. Now, what's always going to be true, though, is that the length of this vector in whichever coordinate system I'm looking at will be exactly the same. Okay, this is what's known as SO symmetry. I'm not going to talk too much about that, but this is what's known as special orthogonal. Orthogonal. There we go. So anyways, all that means is I can rotate my coordinate system any way I want to, but the length of that vector stays the same. Now, we're going to use this upcoming when we start talking about forces, where we're going to draw any type of coordinate system we want to most easily write down the components of these force vectors but we'll talk about that when we actually get there. But just know what the I prime, J prime, I, J, K prime, K, what these do is they specify the direction of our coordinate system. So again, what's happening here is this axis along here, this is my I direction. This along here pointing upward is my J direction. This one along here is my I prime direction. And along this axis then is my I or my J prime direction. Now, note though, that to have a feasible coordinate system, what has to be true is that all of these guys have to be perpendicular to each other. So this axis here is perpendicular to this one is perpendicular to this is perpendicular to this. Even in this coordinate system, the yellow one is perpendicular and the black one here is also perpendicular. So each one of these have to be perpendicular to each other, which means that the I direction and the J direction and the K direction are all mutually perpendicular to each other. So these are components, and these are unit vectors. So now that we know about components, how do we actually then add vectors together using components? So to do that, let's look at a problem. So this problem says that we have 3 vectors. Each one has exactly the same magnitude, so they're all the same length. So vector A here is 22 units long, B is 22 units, and C is 22 units, whatever these units are. Doesn't really matter. 2 of them have the same angle, so A and B are both at an angle counterclockwise from the x-axis by an angle of 45 degrees, while C is at a clockwise rotation of 30 degrees from the reference line. So that means it's at a negative 30 degrees. So here what I want to know is simply what is the sum of these 3 vectors, and I want it in magnitude and direction, and we can give it unit vector notation as well, just for funsies to get a little practice with that. So good. So how do we actually then add these guys mathematically with each other? So let's look at that. So the first thing we're going to do is, as always, draw our picture. So this is always our first thing we have to do. So I'm going to draw my coordinate system here. So here's my coordinate system. So what I know is, well, our first vector, let's draw A, is at an angle of 45 degrees. So that is going to be along this line here. So this is going to be vector A. And again, we know the length of this is 22. Vector B is going to sit right on top of that. So I'm going to try to draw vector B without really getting rid of vector A. So good. This is vector B. And then finally, what I know is that vector C is going to be down at a negative 30 degrees with the same length. So that's going to be about vector C. So these are my 3 vectors together. And let's call this the x-axis, the y-axis. So good. So what I want to do now is what? Add these guys together. So let's go ahead and create a resulting vector R, which is then equal to A plus B plus C. Good. So let's do that. So again, as we said, using the tip to tail method, all we're going to do is redraw our coordinate system. So here is my coordinate system. So it's my x-axis, my y-axis. And again, all we're going to do is start adding these vectors on here. So again, vector A is going to be this guy. So this is vector A. Now from the tip of vector A, I'm going to draw the tail of vector B. So I'm going to draw that 3 in this direction. So 1, 2, 3. So this is vector B. And now I got to move my beautiful face. So I'm going to move that over here. There we go. And now draw from that the tail of vector C going down in this direction. How far did I draw that? So it's 1, 2, 3, about 4 lines. Okay. So 1, 2, 3, 4, something like this. Good. So this is vector C. So again, mathematically wise, our resultant vector, which I'll draw in green here, is going to be the one which points from the tail of the first vector to the tip of the last vector. So this is our vector R. Okay, so this is vector R. So what I want to know then is what is the length of vector R? So what is the overall magnitude of this guy? And then what is this angle here of theta R? Okay. Good. Now, once we have our picture, first thing we're going to do is make some observations. So let's go ahead and make some observations, and then we'll talk about how we actually add these things. So first off, the first thing we know is that what? Based off of our picture here, theta R must be somewhere between 0 and 45 degrees, right? Because if this angle here is 45 degrees, this angle down here is 0, because if it was along the reference line, then that would be 0. So theta R is somewhere between here. So basically, by noting that, it's a good way that if when I calculate my angle at the end of the day, if I find an angle which is not somewhere between 0 and 45, I know something went wrong somewhere. So now I got to go back and fix some signs and do all that good stuff. The next thing is we can also tell that what? The length of this guy is going to be somewhere between what? 44 and 66. Right? So we know that the magnitude of this guy is going to be somewhere between 44 and 66, right? So what would 66 be? 66 would be if all three of these vectors were along the same direction. So if vector C here was also at a 45-degree angle, in that case, then the total length would just be equal to the sum of the three lengths. That's our 66. 45 or 44 in this case would be if what? C was simply equal to 0, so it stopped here. So in that case, it would just be the length of these two guys together. So in this case, I know it's somewhere between 44 and 66. So good. So how do we determine then the length of R? Well, notice that if I drop a perpendicular here from A, right, so let's draw my perpendicular here. Whoop, what happened there? Good. So this distance here is simply equal to the length of AX. And if I draw my perpendicular on this side, this length here then is AY. Now, if I drop a perpendicular here from B, so this is my perpendicular here, this length then across here is then going to be BX, or if I drop my perpendicular here, then this distance here is going to be BX, or sorry, BY. And then finally, if I drop my perpendicular from the yellow one, good, the C down here, this distance then is equal to what? CX, and then drop my perpendicular here. Then this distance here then is CY. Right? Oh, sorry, from up here. Yeah, this one is CY. Let's do a small erase circle. I can get rid of that. Boop. There we go. There we go. So the reason I did that is because, so now if I notice, if I drop our perpendicular here, notice that this total distance here is simply equal to Rx. So what I can notice from here, from this picture, is the fact that Rx here is simply equal to the sum of all three of these. So Rx then is simply equal to then AX plus BX plus then CX. Okay. Now notice on this side then, if I drop again my perpendicular here, so this is 90 degrees, then this distance here then is simply equal to RY. So notice that RY is also equal to AY plus BY plus CY, where CY is simply equal to a negative value. So in this case, I can also note that RY is then equal to then what? AY plus BY plus then CY. And notice if I had a third or fourth vector D, then the Rx would then have plus a DX. And then if I had an RY, then, or if I had a DY, then this would also be equal to plus DY at the end of this. So basically from here, from drawing this picture, what I learned then is that's what? The X component of the resultant vector is simply equal to the sum of all the X components of the vectors which are added together to create this vector. And Ry then is equal to then the sum of all the Y components that create then this vector. So mathematically then, all I have to do then is what? Break each one of these vectors up into its components and then add the components together, where in this case, I'm adding simply like components together. So that means that, for example, if I'm looking at vector A, in this case, I'm going to write down its X component. So AX then is going to be equal to the magnitude of A times cosine of theta A. And then AY is going to be equal to the magnitude of A times sine then of theta A. Vector B, its components then are going to be equal to BX, which is then the magnitude of B times then cosine of theta B. And then BY is going to be equal to the magnitude of vector B times then sine. No, that's a little too small now. That's fine. Sine then of theta B. And then finally, vector C its components then are going to be Cx are going to be equal to the magnitude of vector C times then cosine of theta C. Now the By, let's be a little bit careful with the By. So notice that the By is actually negative. Now, there's two ways we can actually take into this account. Now here, when we look at the cosine portion, we could put in the fact that theta C is equal to a negative value. And then for By, we can again use the fact that the angle itself is negative. So when we have a sine of a negative value, that becomes negative, and we have a cosine of a negative value, that becomes positive. Now, the other way to do it is just to note that this guy is actually equal to a negative value, and just force in by hand that this guy is actually equal to a negative. Now, personally, that's the way I usually do it. So since this guy is negative, I'm going to go ahead and put in that negative sign by hand. And that way, when I put in the angle here, I'm going to use it as a positive 30 degrees instead of as a negative 30 degrees. Because if I use it as a negative, that's going to be a negative and a negative, make it positive, which is going to mess things up. But I like to control the negative signs. I don't want my calculator to do it, mostly just because, for example, if I had it in radian mode instead of degree mode, bad things are going to happen. So I'm just going to do it that way. I'm going to force it by hand, but ultimately, if you trust your calculator, you can do it. I'm going to say don't trust your calculator because your calculator is just, it's kind of stupid. It doesn't think about anything. So good. So good. So from here, I can calculate then Rx. So Rx, as we said, is simply equal to Ax plus Bx plus Cx. So in this case, this is going to be equal to the magnitude of vector A, cosine of theta A, plus then the magnitude of vector B, times then cosine of theta B, plus magnitude of vector C times cosine of theta C. Plug in our numbers. What we find in this case then is this works out to be 50.16 in whatever units that is. And then Ry again is equal to Ay plus By plus Cy, which again is equal to the magnitude of A sine of theta A plus magnitude of B. And then I get a sine of theta B. And then finally, I'm going to put a minus sign because, again, this term is negative. So I get a minus magnitude of C sine of theta C. Plug in my numbers. What I get in this case then is this works out to be about 20.11. Now from here, because we drew our picture and we know the magnitude and the angle, let's go ahead and calculate the magnitude of the vectors. So as we noted on the previous slide, that the magnitude then of vector R is simply equal to the square root of the x component squared then plus the y component squared, right? Pythagorean's theorem. So it's going to be equal to then 50.16 quantity squared plus 20.11 squared square rooted, which means then that the magnitude works out to be about 54. And then the angle theta R is going to be equal to the inverse tangent of Ry divided by Rx. So this is going to be equal then to the inverse tangent of 20.11 divided by 50. Oops. 0.16. Now this is less than 45 degrees because it would be 45 degrees if the top and the bottom were exactly the same. So put in my numbers, what I find in this case is this works out to be about 21.8 degrees. So before we move on and write this in unit vector notation, notice that again, we predicted from our observations that the magnitude would be somewhere between 44 and 66, and that the angle would be somewhere between 0 and 45. Here we find the angle is 21.8, which is somewhere between 0 and 45. And we found that the magnitude was 54, which is indeed between 44 and 66. So our results here match our picture, which is a good thing. Okay. So good. Now, finally, if we wrote this in unit vector notation, we would just say that R then is equal to its x components, which is 50.16 I hat. So this is what tells me it's pointing in the x direction, plus 20.11 j hat, which tells me it's pointing in the y direction. So again, the way I would read this is its x components, because I know whatever shows up in front of I hat is the x component, because this is what tells me it points in the x direction. And then 20.11 would then be the j components, because I know whatever is in front of y is the j is the y component. And again, the j tells me that's what's pointing in the y direction. So this is how we actually add vectors together. So again, to add them together, all we then have to do is add all the like components together. So at the end of the day, I can also write that then vector r was equal to the ax component plus the bx components plus the cx component in the I hat direction, plus then the ay plus by plus cy all in the j hat direction. Good. So last thing we want to talk about is quickly, so now that we know about components, how do we then multiply by a constant? So let's go back to multiplication. So again, we defined that the vector b was equal to c times the vector a. So what does that actually mean in terms of components? So now we know this is c times ax in the I hat direction plus ay in the j hat direction. But this is then equal to c times ax in the I hat direction plus c times ay then in the j hat direction. So what happens then is in component form, if I multiply a vector by a constant c, what that does is it simply rescales each one of the two components by that same constant, so that this is equal to bx in the I hat direction plus then by in the j hat direction. So it just simply means that bx is then c times ax, and then by then is equal to c times ay. Okay. So basically each one of the components is rescaled by exactly that constant of c. So again, if c was equal to 2, ax is twice the size of what it was, and then by is twice the size of ay. What happens then to the magnitude? So the magnitude of vector b then is then simply equal to the square root of, again, bx squared plus by squared, which is then equal to the square root of cax squared plus cay squared. So here I have a c squared, here I have a c squared, I can factor it out. So that's simply equal to the square c times the square root of ax squared plus then ay squared, which is equal to c times the magnitude of vector a. So again, as we said before, what happens is that the size of vector b is c times the size of whatever vector a was. So these are then components. So the components of the force or of the vector are then simply equal to, again, using our trig, they are the projections of the vectors then onto a particular coordinate axis. So again, imagine that you're shining a light over top, as we're doing here, then we get a shadow onto the x-axis. Then ax, the component of ax, is simply the length of it across the x-axis. And if I shine it in the opposite direction, or from the side, then that would also create a shadow, which is then the length of the vector along that particular axis. So that's about it for vectors for now. So again, we will come back to vectors in the other ways to multiply vectors together. So now that we have seen vectors, now we can actually generalize everything we did from chapter 2 into multiple dimensions. So this is what we're going to do next time. So on Monday, we're then going to take all of this information, all of this knowledge about vectors, and then generalize it into multiple dimensions. So we'll talk about all of the different things we already talked about. So we'll talk about position again, displacement, velocity, acceleration. How do all these things actually generalize into multiple dimensions? So that's what we're going to do on Monday.